Okay, I think we're recording.
Okay. So I'm trying to follow from last time with my plans to talk about zeta types and how it applies to classification of torsors over finite fields. Let's see. One thing that came up last time was we were thinking about double negation topologies in topos theory. And I just want to mention an example. You know, we were trying to think of examples that might be interesting. I just want to mention one example, not try to do it right now. I just want to mention an example that we should think about, because it is similar to an example that you were, it's somehow similar in, I don't know, in spirit, moral intention to some examples that you and I were trying to bring up last time. So the example I have in mind here is start out with a pre-sheaf topos, or same thing, a set-valued functor topos on the site category that's just a single object category. So it's really just a monoid. And let's say the monoid is the free monoid on one generator. And let's see, since that monoid is equal to its opposite, isomorphic to its opposite monoid, that means that it doesn't pay very much to try to decide whether you should be talking about the set-valued functor category or the pre-sheaf category, you know, the site or the co-site, because they're both the same, basically. Yeah, so that's a pre-sheaf topos. And as a pre-sheaf topos, it's subject to Diaconescu's theorem, which tells you something about pre-sheaf toposes. So that's an interesting thing to learn about in there. But then you end up taking, well, one of the things that's interesting to do is to take the double negation topology of this pre-sheaf topos, the double negation topos of this pre-sheaf topos. So that's the example. It's good to think about, and it might bring out things that you were trying to hint at, and things that I was trying to hint at last time. Again, we were talking about philosophical things like I probably forgot to say being versus becoming, but we were talking about that kind of thing, you know, like how Parmenides is very interested in being, things that just are, and whereas Heraclitus, however you pronounce it, is very interested in becoming, just things eternally becoming and becoming and becoming. And this idea that the double negation topology sort of mediates between those viewpoints in some sense. On the other hand, let me just mention another thing that's interesting to learn about is, you know, what in the world is the double negation topology? Because it's not exactly, in any terribly obvious way, it's not exactly an adjoint functor, like to the inclusion of Boolean toposes among arbitrary toposes. It is some sort of, you know, best Boolean approximation to a topos, but in some funny sense. And
is there an adjoint functor to? Did you just possibly existing? Boolean application.
I think it's a tricky question. I think the answer is mostly no. I think the like size problems that, but there might be circumstances, you know, if we change the rules a little bit, we might be able to come up with something. But in general, it's in the classic context where I'm thinking of, I think neither adjoint exists, neither a right adjoint nor a left adjoint, if I remember correctly. But anyway, that's all I wanted to just say, that's an interesting example to think about. We might want to come back to that at some point. Taking that pre-sheaf topos and understanding its double negation topology, and perhaps thinking about the philosophy of how, that involves becoming. You start with becoming, but then it becomes being.
Then it's stuck.
Yeah, exactly. Okay. So
I'll resist saying my guess as to what happens to the topos of n sets when you do this to it, or should I say my guess?
you could say there's something you can say. Go ahead. That's a good.
I mean, it seems like you're pushing me to saying that you get z sets.
I think that's right, but there's something very funny about the way it happens.
Yeah, I'm not claiming I understand why, so I would enjoy going through it sometime.
Sure, right. It does sound like, oh, that would be the simplest thing in the world, but it's actually tricky.
Okay.
Definitely worth learning about at some point. But let's see. Okay, so another thing I want to mention right now, following up on things we were talking about last time, and this is one of those kind of things that I should really go back and listen to what I said last time, to see to what extent I said it the right way or left things out, because I mean, we were talking about zeta types, which are like or zeta structure types, at least, are set valued functors on the groupoid of finite sets. I mean, I guess those are actually the same thing as Maclaurin types, or Joyal's structure types, but you manipulate them differently using Dirichlet convolution instead of Maclaurin convolution or something like that. But at some point in the discussion, and maybe I didn't make it clear where in the discussion, but at some point in the discussion, it seems like I switched from thinking about, let's see, at first I was thinking about so did I say it right today? Did I say Preci's on the groupoid of finite sets, or set valued functors on the groupoid of finite sets? Again, but then we were thinking about set valued functors on the groupoid of finite fields. That's related to this in some funny way. But then I think the sleight of hand that I didn't handle very well is that somehow we switched to thinking about set valued functors on the category of finite fields, because that's where you get to play these games with the double negation topology and stuff like that. So there's some funny interaction between the set valued functors on the groupoid of finite fields and the set valued functors on the category of finite fields. And in some sense, the set valued functors on the category of finite fields are better than the set valued functors on the groupoid of finite sets. But from the work that you and I did some decades ago, this whole categorified zeta function idea, categorified zeta series, that lives at the level of the set valued functors on the groupoid of finite fields. But the nicer categorified zeta series are the ones that actually live on the category of finite fields. And again, what's nice about them is that you can play this double negation topology game, and so if you work one prime at a time, that what you're doing is you're ending up with with the topos of continuous actions of the Frobenius group. I'm not sure if Frobenius group is the best or correct terminology for that, but it's this thing that's generated by the Frobenius automorphism.
Profinitely generated, I guess.
Say it again.
Profinitely
generated. Yes.
Yeah.
Yes. So it's like
And
a
then
profinite group, and it's some profinite cousin of Z or something like that. And so there's actually a lot of intricate games to study there, and maybe we should study them sometimes. But the basic conceptual idea, and you basically mentioned this last time, is that by means of playing these games with the double negation topology in the context of the categorified zeta series, you can make the conceptual transition from the categorified zeta series to the categorified L series. Because that's what these categorified L series really are all about, that for each prime, you have this Frobenius action. And probably a lot more to say about that, but that's
what is there to say about species on the groupoid of finite fields? Sorry, did I say that? What is there to say about set valued functors on the groupoid of finite fields? So you get that's enough to get you one of these zeta functions.
Right by this, yes. And again, I think you said that that you actually wrote this up.
I think that's what I wrote up. But the funny thing is that there I was actually, to show stuff about them, I was actually using the Frobenius. And the way I was using it, I guess, was that, like, you think of the fp to the n, the field with p to the n elements, as the fixed points of the nth power of the Frobenius. I think that's how I was acting on, I guess, on the algebraic closure of FP or something like that.
I mean, maybe we should go back at some point and read what you wrote there, because
it's.
I mean, what you're describing works in the right context, but see, I mean, right? So if you have a set valued functor on the category of finite fields, then that's a set valued functor on the groupoid of finite fields, but with some extra structure, which is this, action by the, let's see, the action, or whatever you call it, by the non-invertible homomorphisms between the finite fields.
It's been a while since I keep looking at that.
Yeah.
We wrote over and over again, and
it could be it could be it could be that that you somehow are implicitly using the category, even if you're doing it correctly with the groupoid. There could be, I don't know, it would be worth, now that we're discussing it, it would be worth, at least for me, maybe for you too, to go back and read that again and see what's going on there, and see if we can bring out the whole conceptual story.
I think I was somehow implicitly,
yes,
I think I was focusing on particular
examples,
and those examples have this property actually that they extend to functors on the category, and I was probably using
that. Could easily be it. I mean, right, we should check
things,
because it would be really good to identify what you're really using. If you were, if you were using things that work in particular examples, it'd be to identify that.
Now, like
So,
a class of examples would be like a structure on a finite set would be a way of making it into a simple commutative ring, and then looking at, so making it into some ring R, and then looking at the R points of some scheme. And so those are, so that I think, well, the fact that R points transform nicely under non-invertible maps between commutative rings is that, yeah, it's true. And so I think, yeah, I think that we/me was secretly using some stuff about the non-invertible maps. Yep.
yeah, so I hope I can just get a link from you or something where I can read this. Send to me an email or something like that. Let me also mention, just before we try to get into the more detailed number theoretic stuff, let me just mention another vague conceptual guess that I have here, which is that, so I've been talking about this double negation topology on the site, on the co-site category of finite fields, or perhaps especially finite fields of characteristic P. It's a little bit neater, perhaps, to do it that way. That double negation topology and the way it, connects to this whole idea of categorified L series versus categorified zeta series. It feels to me like, in miniature, this is like some important part of the story of étale topologies, the étale toposes and stuff like that. That somehow, that action of the Frobenius is somehow really, right? We're seeing it kind of, I don't know, in sort of miniature form here. But I think that's really going to be connected in some way with the étale topos, and the way that the étale topos is related to the Zariski topos, except the étale topos has this extra Galois action involved, or something like that. So that's supposed to be vague at this point, but it's a vague guess that this game involving the double negation topology on the co-site category of finite fields of characteristic P, I think that's related in some way that would be good to understand to the idea of the étale topology, the étale topos or étale toposes. So okay, so now let me go ahead and let's try to do some more concrete games here with this. So let's just, so yeah, so okay, so now we're going to take some specific categorified zeta types or something like that, which will probably have this extra nice property that we were just groping towards trying to understand. So but on the other hand, these zeta types that we're about to look at, they may be zeta stuff types rather than zeta structure types. So that's a whole issue that we'll have to deal with. So perhaps as usual, we certainly won't be working at an extremely rigorous level of rigor, but I'm not sure how unrigorous we'll be getting here. So let's see. So let me try to give a couple of parallel examples, including some easy examples. of the kinds of categorified zeta series that we're interested in here. So what would be an example? We could have like, yeah, I think what I want to do is I want to start off with basically a 2-rig and get a categorified zeta series from a 2-rig. And yeah, and this is supposed to be, a way of looking at all the sorts of examples that we've thought about previously, decades ago. So, but perhaps a slightly more sophisticated viewpoint about it, or a slightly more something viewpoint about it. So, so now I say 2 rigs, but which, in some ways that sounds scary, but it's supposed to be, really easy 2 rigs from the point of view of algebraic geometry. So let's say, for example, right? I mean, so these 2 rigs are like algebraic stand-ins for geometric objects, which are perhaps called algebraic stacks or something like that. And among the algebraic stacks are these algebraic varieties or algebraic schemes, whatever we call them. So we're going to have some very nice, simple algebraic varieties involved here. So, for example, there's this algebraic variety, I guess the integers adjoin the square root of -1. And right, so we get this algebraic variety is where we get the Gaussian zeta function or the Gaussian L series.
Why are you calling that an algebraic variety? It's the
sorry, this is a commutative ring, so it's an so it's so it corresponds to an affine algebraic variety.
Okay, is that true? Okay, yeah, okay. Do people even talk about affine algebraic varieties over a non?
Well, perhaps they call it an affine scheme or something like that.
Yeah, okay, I would prefer to call it that. Okay, fine.
Okay, an affine scheme. Right, the spectrum of this commutative ring formally, yeah, an affine scheme. And so this is going to be one of our examples. But how do we make this into a 2-rig? Well, we just take the modulus of this. Okay.
Okay.
So let's take that. So maybe I'll write it as the modulus of that. And basically what we're going to do with this is we're going to hom this. I mean, right, what am I trying to say? So if you think of this as an algebraic, if you think of this as a scheme, then what the zeta function is doing is it's counting the points over finite fields. And we're just going to kind of fancify that in a bunch of ways and dualize it and stuff like that.
Okay.
Hopefully I won't get myself that badly confused when I try to do this, but I will get myself confused at various points and we'll have to try to get myself unconfused. So, maybe we should just play around with the numerology of this for a moment. Counting the points over the finite fields. So how does that work? So let's see. So we have like the powers of 2. I mean, we have F2, F4, F16, etc. And then we have, like F3 and F9 and F27, etc. And then we have
8 for some reason.
what? I skipped 8. Sorry. No, wait a minute. Oh, no, maybe I did. Okay, wait a minute. Am I screwing up here? Don't tell me. Let me think. What am I trying to say? Yeah, no, I skipped 8 for, I guess, for stupid reasons. Yeah, there certainly is
A better reason than not remembering that 8 was a power of 2, but still,
yeah, slightly better. So,
I think I know something about the reason. Okay.
yeah.
Yep.
And then perhaps
5. Let's try 3 different kinds of things that happen.
Well, yeah, I mean, these are the first 3 primes, but I think these demonstrate the different things that can happen. I guess, what's some of the traditional terminology? This is going to be ramified.
Yep.
This is going to be maybe inert, is that right? And this is going to be split.
Oh, yes.
So, right. So the inert ones, I think, are going to have no points. Is that right? Over right. There's no. So that's right. That right. That's what happens over the 3-element field. There are no points of this variety. Whereas in the split case, there are some. And I guess there's 2, is that right? And maybe in the ramified case, maybe there's just 1. I guess that's right.
Always just 1 or just 1? I don't know. I'm bad at this. There is 1.
Well, I mean, it's such a small field. I exhaustively,
Yeah, no, in that case, I definitely. No, I meant all the other higher powers. So yeah, so. But I think you may be right. Let's see. So you need a square root of -1.
Well, so I mean, in the ramified case and in the split case, the roots.
Yeah, I guess that's right.
The roots, such as they are, have already arrived. You're not going right. I mean, there's limitations. You can't have more than n roots of an nth degree thing or something like that. So in the split case, we've already got all the roots there. In the ramified case, we've got all the roots there if you count multiplicities or something like that. But in the inert case, they haven't arrived yet. So I think they're going to arrive at the field of size 9.
Oh.
So am I saying this right? So let's see, it's going to be 2. And then, the 27 element field is not an extension of the 9 element field. So I think it goes back to, right? I mean, it's really not, it's not a monotone sequence in the.
Right, the true, yeah, the true post set is not this linear.
Yes, set. That's right. That's right. That's right. So is it just going to go like this or something like that? Did I make any stupid mistakes here? In some sense, this numerology is going to, if I didn't screw up in some stupid way, this numerology is what gets this data, this numerological data is what gets turned into the zeta series. Okay, so I mean, that might be the classic example that might be the only classic example that we need. Like, let's just do one more example for a good, right? Our usual, like, trying to pick a smattering of examples that exhibit all the behavior in the world. So I guess my other example would be, so this first algebraic variety that we looked at was very small and finite. It wasn't discrete and finite, but it was very small and finite. It's kind of, morally 2 points. So those 2 points are sort of hard to, it's not like two discrete separate points, but it's sort of like a 2-point space. But let's try the projective line, or let's try the affine line. That'll be a little bit easier. So the affine line is like what? It's, as a commutative ring, it's just polynomials in one generator.
Yep.
And so, by the way, one of the things that I'm not completely mystified by, but I'm not sure exactly why I'm doing it this way, is why am I working over Z at this point? Well, like there have been times when I've been working over the rationals instead of over the integers. But if I'm just naively looking for points over finite fields, then it's going to work better if I work over the integers instead of over the rationals.
Yeah.
There must be some, compensating game you can play if you're working over the rationals, but for the moment I'm trying this. So yeah, so I just take modules of this commutative ring, and that's my 2 rig. And but let's go back for a second. And right, I mean, it's I said that we're working with 2 rigs, but of course when we did the first example, we didn't really think of it in terms of the 2 rig. We just thought in terms of the ring.
Yep.
So let's do this second example the same way. Let's just try to do some numerology here. So the F, I guess it's like 2, 4, 8. Is that right? It's just, and this is like, yeah, it's I guess
number of elements. Yeah. Yeah, that's a nice, easy one.
Okay. And that gets turned into a zeta function. Am I supposed to instantly be able to remember what that zeta function looks like? I'm not even thinking about it at the moment. I'm trying to go on to my example, my next example, right? These are the only 2 examples that I'm using for like context. And my next example is supposed to be the example that I'm really interested in. So the next example is supposed to be it's supposed to be not an algebraic variety, but an algebraic stack.
Mm-hmm.
And it's supposed to be the algebraic stack of Z mod 3 torsions. And I guess I'm gonna think of that. So how do I write that down as a 2 rig? So I'm gonna take let's see. That's agonizing over silly choices about notation here. So it's like Z. What am I trying to say? I'm trying to say take representations, I guess representations over the ring Z of the group Z mod 3. But I guess I'm supposed to do this comodules. So how does this work? How does this work?
Co-modules of Z mod 3 over Z.
Yeah, I think that's how we're going to do it. But so how does this go? Let's see. So at first I was thinking that I'm being unnecessarily over precise here, but but maybe not. Maybe there are weird things that can happen if I do this the wrong way. Like if I, if I took the modules instead of the comodules or something like that. There's Fourier duality things that can have peculiar effects. So yeah, so what am I trying to say here? We're trying to take, I mean, the key issue may be trying to figure out the right notation for this. So let's see. Okay, so right. Okay. So I'm trying. Oh, okay, don't tell me. Let me see if I can get this right. So I'm trying to say that we're going to think of Z mod 3 as an affine algebraic group, and an affine algebraic group, yes, of a very simple kind. So how do I say it? Okay, maybe I'll say it this way. Let's see. So maybe I'll say Z. Yeah, now I'm really agonizing over whether I should say, the Cartesian power or the direct sum power of 3 copies of Z. But of course, they're really the same thing. So that is okay, right. So this is right. This is a right. This is a bicommutative Hopf algebra. And the fact that it's bicommutative is sort of annoying.
Yeah.
Okay. Right, because it makes it hard for me to figure out which is the right type of Fourier duality to work on. But maybe part of the point is here is that there is a slightly more general example that I should do here, which is I should take, let's take G to be a finite group.
Good.
Not necessarily abelian, and that will make it a little bit easier to keep track of, the 2 Fourier dual Hopf algebras here, because one will be co-commutative and one will be commutative.
Yep.
So G is going to be a finite group here, I think. And now we're going to take.
So as a scheme, so it's going to be a group. You're trying to turn it into an affine group scheme. I know you're not saying it this way, which and
Yes.
so as a mere scheme, it's just a zero-dimensional scheme of a boring sort. So its function ring is you think of it as like Z to the G.
Yes. All right. So okay. So let's call it that way. Or again, I was thinking of maybe I'm not going to do it with the direct sum there, but right. So this is right. Functions on G. Now it is a little bit peculiar here that it's integer valued functions. That seems like a slightly unfamiliar thing that I don't usually think about, integer valued function rings, but maybe it's the right thing to do. So let's try it. Functions on G, and perhaps we should emphasize that they're integer valued. And so this is a, don't tell me, this is a commutative Hopf algebra. It has a Fourier dual that's a co-commutative Hopf algebra. Sorry.
Yeah, I remember how horribly confused we got about using Z mod 3 as an example, and it's
right. For the moment, I seem to have shunted aside the case G being Z mod 3.
Right. Well, as long as you don't call it Z mod 3, just call it G. And only, then you're less likely to get confused. Yeah. So yeah, it's a commutative Hopf algebra, and then we want to look at its co-modules. which are
Right,
sort of
but just to orient myself, let me say a couple of things about what's going on here. So like there's a, what do we call these? Like a multiplication and a co-multiplication. So yeah, multiplication is pointwise. Whereas in the dual Hopf algebra, the multiplication is a convolution thing, right?
Yep.
Okay. And the co-multiplication, is there some conceptual, okay, just give me 30 seconds to just think about how I might try to describe the co-multiplication. Well, okay, I do have it. Do I? Yeah, okay, I can say my answer.
Yep.
So it's somehow it's just coming.
I have my answer in my head.
What?
have my answer too. I'm keeping
okay.
it in my head.
Okay, well, I don't have a more detailed answer just then that it's coming from the multiplication on G.
Yeah. So it's just take G times G goes to G, and that gives you contravariantly something from Z mod Z to the G back to Z to the G tensor Z to the G. You can think of it that.
Right. Okay. So, but I'm just going to write down here. It comes from multiplication on G.
Yep. That's the interesting part.
Okay. And now we're going to take comodules of this Hopf algebra.
Uh-huh.
So I have to think about what that's like. So let's see. Okay, let me say let me call this commutative Hopf algebra. Let me call it H for now. So we're going to take H comodules, and we're going to make that into a 2-rig. And so by the way, so what are we going to do with all these 2 rigs? Well, we're just going to hom them into the 2 rigs that we get by taking the vector spaces over a finite field. Except that, of course, morally, what we might really be doing is we might really be homming them into the vector spaces over the algebraic closure of the finite fields. The algebraic closures of the finite fields. But that's that whole game about, the double negation topology and everything like that we're really interested in. So, yeah, but right. So part of the point is that this process of passing from the commutative ring, or equivalently the affine scheme, passing to the modules of that commutative ring, that's a good passage. And the 2-rig homomorphisms that you're going to end up with are basically the same as the ring homomorphisms that you had in the first place. So, this is just, so for our first 2 examples, it seems like we just, made things unnecessarily sophisticated. But for this next example, it's probably, about the right level of sophistication.
So we're doing 2 rigs that are enriched over abelian groups right now.
Yes, that's right. That's right. That's right. And and it might change if I suddenly realize that I'm doing something wrong, and maybe I'll have to switch somehow to rational vector spaces instead of abelian groups or something like that. But for the moment, we are doing it with abelian groups. And
it looks like it wants to be that, because I mean things like vector spaces over FQ, it's enriched. Well, it's enriched over vector spaces of FQ, but it's not enriched over any one particular thing, except for abelian groups. It's certainly not rational vector spaces. So yeah.
Right, but on the other hand, maybe there's some really sophisticated game that I'm supposed to be playing that involves, the p-adics and the adels or something like that. I don't know. But at the moment, I'm trying to economize on that kind of conceptual sophistication. Right, but so in particular, that numerology that we did above, we just did that thinking naively about the algebraic varieties, but we could have, we should have gotten the same answers if we thought of it in terms of two rigs and, the points of the spectrums of the two rigs. Okay, so we're going to try this. Okay.
So one thing you're saying is that ring homomorphisms from a ring R to FQ correspond to two rig homomorphisms from modules of R to modules of FQ.
Yes. So this passage from the
that's the
this passage from the commutative ring to the module category for the passage from the commutative rig to the commutative two rig. I'm saying that that's a full and faithful two functor or something like that. I hope I said that correctly. I hope I'm saying it in an appropriate level of generality where it's correct.
And it's covariant.
And it's covariant, yes, and it's sort of all on the algebraic side. You know what I mean? It's like, this whole algebraic geometry duality between algebra and geometry. And here we're leaping up in conceptual dimension from, one rigs to two rigs, but we're staying on the exact same side of the algebraic geometric duality. We're still on the algebraic side of the algebraic geometry, algebraico-geometric duality. We're still on the algebraic side when we pass from the one rig to the two rig.
And the way that a map between rings gives a map between two rigs is the sort of it's the left adjoint of the pulling back.
Yes, right. So right, and you already asked this question, and I sort of tried to answer it, but it's good that we give the answer more explicitly. That yes, it's this covariant thing. So what are you saying? Let me hear your answer again, and let me think about if I understand your. Say it again.
So
you've got a ring
homomorphism. I've got a ring homomorphism from R to S.
Yes.
Getting a two rig map from modules of R to modules of S.
Yes.
The left adjoint of the one that I find somewhat simpler, which is the one which is pulling back along the map from R to S. So there's this sort of very nice thing from S modules back to R modules, which has both a left and a right adjoint. And here we want the left adjoint because we want it to be preserving colimits. Well, that's one way to see why we want that.
Right, but also this is like the only obvious thing that actually gives you a two rig homomorphism.
Yeah, right.
And it gives you it covariantly. Yes. So yes. Yes. There's probably all sorts of good ways of thinking about this process that I'm not quite picturing in my mind correctly at the moment, but yeah.
Okay. Yep.
So,
Okay. So now anyway.
so all that numerology we did was,
Right.
we're now giving this sophisticated reinterpretation of all that numerology in terms of these two rigs instead of the one rig. Okay, now what were you saying?
And now we're leaving the safe waters of two rigs that are secretly just coming from one rig, so we're going into something.
That's right. That's right. And so yeah, maybe we should also try to say what the how is this co-module category? How does it become a two rig? And what is the tensor product? And it's basically just what I think you and I both think of as just the tensor product of group representations. In other words, right, the tensor product of group representations is mostly if you basically forget that they're group representations. Just think of the underlying vector spaces and tensor those, and then that becomes in some. Am I saying this right? Yeah, I think that's right. I think I said that right. So I'm not sure how to say that exactly in this context where we were thinking of, where we have this intuitive idea of representations, but here we're thinking of those co-modules. But it's basically that idea that when you tensor representations, you don't even think of them as representations. You think of them as vector spaces and you tensor. So that's how this is becoming a. If you think about that in the right way, that's secretly telling us how to think of this co-module category as a two rig.
Where our vector spaces are really abelian groups, right? Just to be annoying.
That's right. That's right.
Okay.
But you mean just they're being annoying by being abelian groups, or no, you're being annoying by mentioning it, or
yeah, I'm being annoying by pedantically pointing out that you're saying vector space for these.
Well, things. But it's a combination of all these things.
It's annoying at all.
it's everything's
okay. Fine. Okay.
Fine. It's probably my fault.
Okay.
Yeah. So right. So what we've just said is in some sense the to the extent that we've said it correctly, this is sort of the formal definition that we're paying lip service to before we jump in and try to calculate things in every intuitive way that we can.
Right.
So right, let's try to do this now. But we still haven't revealed the secret that G is actually Z-mod 3 yet. We're still thinking of G as quite possibly a non-abelian finite group. Right. So I'm going to try an approach here to thinking about this. And and I have been getting myself pretty confused about this at various points in the past couple of weeks, but I think it's a really good thing to try to straighten out. And I'm going to try a number of approaches here. So the first approach I'm going to take here is, I have a feeling that this is in some sense a geometric approach as compared to an algebraic approach. But what's the idea? The idea is I'm going to be thinking in terms of, what am I trying to say? Well, so first of all, right. One of the things we're supposed to be reminding ourselves of here, I don't remember whether you said this out loud, I probably didn't say it out loud today, is, what is this representation category doing as a two rig? So it's basically, it's the walking G towards her, in some sense. I think, again, there are things to prove there, but I think that's right. That's my moral assumption at the moment, that this comodular 2-rig is the walking G torser. Maybe I should call this H sub G. It's depending on this finite group G. Okay.
Uh-huh.
And it is the walking G torser. I think that's the moral assumption I'm making at the moment. So so I'm trying to think about what G torsors are over a finite field or over the algebraic closure of a finite field, et cetera, et cetera, et cetera.
Uh-huh.
And so what am I trying to say here? So yeah, so a right, I'm trying to use some geometric thinking here, and yeah, I'm also noticing ways I could easily fall into traps here, but right, I mean, G torsors are like principal fiber bundles, morally like principal fiber bundles with fiber G.
Uh-huh.
And so I'm trying to use my, naive homotopy theory analogy. I'm thinking about like, right, I guess what I'm actually thinking about is I'm trying to picture little covering spaces covering the circle. Because, right, there's this vague idea that because of the Frobenius nature of these automorphisms of finite fields, that these spectrums of finite fields are like little circles.
Uh-huh.
Because they're, they're the absolute Galois group, the Galois group of the algebraic closure holding the finite field fixed, is this, pro-cyclic group, pro-cyclically generated by the Frobenius or something like that. So it's like an étal homotopy group or something like that, some kind of moral fundamental group. And so right, having a moral fundamental group that's morally as pro-cyclic is that is pro-cyclic or whatever we call it, is it's like being a circle, because the fundamental group of the circle is Z, is cyclic. So so how would you classify the finite? How would you classify the G torsors over the circle, where G is a finite group?
Uh-huh. So I'd imagine you have this holonomy around the circle.
Yeah, exactly.
And so that's basically,
where does that live? Where does that holonomy live?
It's an element of G, the
Yes.
group, and then there's this category of such things, and the
I guess we can think of it as maybe it's slightly preferable to think of it as a groupoid at this point.
Yeah. Sorry, a groupoid is probably what I meant to say, and then two of them are an isomorphism between them is like a conjugation carrying one element of the group to another one.
Yes.
So it's a
yes. So you have classified these by the conjugacy classes in G. And the automorphism group of, for an object, for a torsor in any particular, where the holonomial is any particular conjugate class, the automorphism group of that torsor is the centralizer. Is that what's called the centralizer of the element in that conjugate class?
Yeah.
So that's a big part of the story. Big part of the story. So what are we? Yeah. So what are we saying there? We're getting a groupoid. It's the groupoid of elements of the group, and that, and right, and this, things are tame enough that we should be able to just pretend that these pro-cyclic things are really cyclic, and everything going on here. So yeah, so I think we're saying that we really are classifying the torsors over these finite fields by elements of G. But now we're just trying to clarify how this is supposed to give us a zeta type, and in particular a sort of zeta stuff type or something like that.
So we want to get a,
and it may be right. It may be one of these, extra nice zeta types where you can actually transport things along homomorphisms of finite fields instead of just isomorphisms of finite fields. Sorry, what are you saying?
so you got this groupoid.
Yes.
Where the objects are elements of G, and the automorphisms of any one are the centralizer. Sorry, the objects are skeletalizing. Objects are conjugacy classes.
Yes.
Yeah. So what?
Can I ask a stupid question? Well, sorry, I want to ask.
So how is that? How is that
finish,
groupoid connected to the various things we've been talking about, like the 2-rig of comodules of this?
That's one of the things I'm trying to clarify. That's one of the things I'm trying to clarify. So,
okay,
right at the moment we're not. Right at the moment we're taking a more intuitive picture, and we haven't connected with that 2-rig picture yet, but we really, really want to. But go ahead. Yeah.
So how does this? Well, okay, but even if we're doing it intuitively, how are we going to use this way of thinking about things to figure out a zeta stuff type? So we're going to try to put some stuff on a finite field. Sorry, we're going to try to put some we're going to try to put some stuff on a finite field that has something or other to do with this groupoid. And what is it supposed to be? The representations of that groupoid over that finite field, or what? I'm just wildly guessing.
Can you say it again? I didn't do a good job of listening.
Okay, we have this groupoid.
Which probably means I'm not going to have a good answer yet, but I really want to figure this out. I really want to understand.
Okay.
So
yeah.
Go ahead.
Okay, so we've got this groupoid. I won't describe it again, but
yes.
You know what I mean, right? Okay, so
yes.
And then we're trying somehow from that, we're trying to get a zeta stuff type.
From the knowledge of all of these groupoids. Yeah.
All of these groupoids?
Well, okay, so you're going to try to just get one like Euler factor or something like that?
Wait, my groupoid had nothing to do with, my groupoid had nothing to do with the choice of field. It was just this groupoid where the objects are conjugacy classes in G, and And the isomorphisms, the automorphisms are centralizer. The automorphism groups are centralizer groups. That's some groupoid. It just depends on G.
Okay, but right. So so far we've just been fixing one finite field.
Well, what I said had nothing to do with any finite field. It just was
but it
about
secretly did. It secretly did. It's just that
oh yeah, I guess it did. Yeah, okay, it did. Right. Okay, yeah,
right,
because the whole point of this circle is that it came from a finite field. Okay, but it didn't. Yeah, okay, but it mysteriously doesn't. The stuff I said doesn't depend. It doesn't.
That's
it's
right.
Independent of the finite field. Yeah.
That's right, and independent in a funny way, and there's all sorts of confusing things going on here. But yes, So right, that was a good question to ask. Right, because there are these funny things going on here where.
But how am I supposed to think of it? How am I supposed to How am I supposed to describe this groupoid in a way that sounds like it involves the finite field? It's supposed to be the.
Well, right, that's the question. I mean,
okay. That is, it's supposed to be something like the. What is it?
I'm struggling with I'm struggling with this with myself. I have some ideas, but they're so confused in my mind. I'm not sure I can give you any good answers yet. But do you want? I mean, if you want to try to say stuff about it, that's great.
Okay. Well, no. I mean, at least I feel slightly better that you're confused because I was thinking I was just like had just like forgotten to say. You popped over to this intuitive way of thinking. That was supposed to be an intuitive way of thinking about something that involved the finite field, something about G torsors over spec of the finite field.
Yeah.
Where we think of spec in this Étale, people normally think of it as like with this Étale topology, something like that.
Yeah, one of the things that's really getting me confused at the moment, but it's going to be important to clarify, is there seem to be two conceptually different ways in which the Frobenius action or some Frobenius action is showing up here. One way is in understanding what these torsors are over finite fields, but then the other way is in how that acts. The Frobenius is going to act on these torsors, and that's going to be part of the zeta. Again, I'm a little bit confused about what's going on here, but we're supposed to try to work at getting unconfused here. I mean, in principle, I think we have definitions and things to ground us if we think about it hard enough, but like I say, I'm going to be trying some intuitive things, and they maybe get me into confusion, and maybe have to work back and struggle back.
So
yeah.
Okay. So we have this very concretely described groupoid where the objects are conjugacy classes in G, and the automorphisms are. The automorphism groups of those objects are these centralizers. Okay, but that was supposed to be like the result of like a hand-wavy calculation. And I think what we were calculating was something like the groupoid of two rig maps from cMod of H to vector spaces over a finite field. Those two rig maps from H to vector spaces over your finite field, those were supposed to be the G torsors over the field.
Yes.
And we were wanting to understand for some reason, we were just wanting to understand the groupoid of such things.
Yes.
Any other kind of morphisms besides automorphisms or what? I don't know. But
I don't think there are going to be other
okay.
ones.
Okay.
I think.
Okay. No. I think maybe you knew all this, but anyway, I'd sort of like forgotten what what was going on here. So basically you could say like,
Oh, it's
I'm
so
going to
easy to get
calculate.
confused. It's so easy for me to get confused. But go ahead, yeah.
Okay, yeah. So, but anyway, like some attempt to tell the story in a seemingly linear manner is like, we were busy getting ready to calculate the groupoid of two rig maps from cMod Z to the G. That's what you're calling H.
Yes.
To
Sub G,
vector
yeah.
spaces over FQ for some prime power Q. And if we knew what we were doing, maybe we could actually, I mean, that's a well-defined thing. That's a well-defined groupoid. So we could calculate it if we knew what we were doing, and maybe the answer would pop out to be this other groupoid that we've been talking about, which is of conjugacy classes, and the morphisms are these living in these centralizers. I mean, that's like a possible answer to the original question.
Well, there's some connection. There's going to be some connection.
Yes, right.
But I'm very confused about what the connection is. I mean, so right. So I mean, one of the things that we're trying to do here is, again, so we're sort of close to thinking about humming this two rig into the vector spaces over the finite field. But then, right, depending on whether we emphasize the categorified L series versus the categorified zeta series, it's like, what am I trying to say? That we're going to be, we probably want to be thinking about humming the two rig of humming the co-module two rig H sub G. We probably want to hum that into the two rig of vector spaces over the algebraic closure of the finite fields. And then the Frobenius will act on that. And so let me just say, I'm trying to say, I'm depending on the situation, sometimes it's not a good idea to mention all the ways that you can get confused. But I am, at the moment, I'm trying to mention a bunch of possible ways that I can get myself confused here and can get you confused possibly too. So one of the ways that I'm trying to emphasize here is that, what am I trying to say? They're just different group actions that I'm finding myself getting confused between. And I have a feeling that they're dual in some way or something like that. So there's this conjugation action that we've been talking about. The conjugation action of G on the elements of G. By the way, let me ask you that. So you mentioned this groupoid of elements of G, right? So let me just ask, think of that as the groupoid of elements of G. That's a groupoid. It's a nice finite groupoid because G was finite. So it should have a nice groupoid cardinality, and that groupoid cardinality might be relevant because we're doing all sorts of,
Right. I was, yeah.
So what is the, let's just try to calculate the groupoid cardinality.
I think it's like 1, because you're taking G, the group G, and weakly modding out by G.
That's right.
Acting by conjugation. So yeah.
I think that's right. I think that's 1, which I think that might be making me suspect that if we de-groupoidify the zeta type that we're going to end up with, we might again get like the Riemann zeta function or something like that. Don't quote me on that yet, but I think something like that might happen because of that, funny cancellation that you just mentioned. That we have G acting on G. So, sort of dividing the size of G by the size of G, and we're getting 1, right? That's the group here. Even though that, right, and it's happening in a interestingly lumpy way that, we have some fat conjugate classes and some skinny conjugate classes, but somehow it all just balances out and you get this boring answer 1. And that reminds me of all sorts of, that reminds me of this, funny way, right? I always thought it was funny that the structure type of finite fields ends up in a funny, lumpy, cancellation-y way. ends up giving the Riemann zeta function. So I don't know. I just wanted to mention that there's some funny things going on here that remind me of some other funny things that I don't understand. So
yeah, that funny business had something to do with automorphism groups of simple rings. I did in this paper we wrote, which I sent you the link to.
Yeah.
It's probably like not good for a publishable paper because it starts out with like a really long calculation of just like showing, wow, it's amazing that we get one out of this really complicated
right
calculation, and then eventually we come around back to like saying why it has to work out to be equal one. But that was not, yeah. But so that was definitely.
But that doesn't guarantee that we actually found the real reason why it works out to be one.
Well, okay, but anyway, that
yeah.
had nothing to do with any particular choice of finite group G. So
right.
Well,
so
it didn't. So there's something.
It didn't appear to have anything to do with any particular.
Okay. Yeah.
All right. So. All right. So. Yeah, we still got a fair amount of time left to try to confuse ourselves. Yeah, go ahead.
Yeah, you're listing ways that we could get confused. So
right,
you get it all organized.
right. So, well, okay, right. In fact, let's sort of pause in this direction for a moment. So, what we've done here so far is we're trying to set up one way that we can one viewpoint that we can explore. That you know, if we continue in that vein that we were just talking about, then we should be able to come up with an answer for what the zeta type for the G torsors should be. We haven't done that yet, but we've sort of set up a project there that we should be able to do that. Now, there's a second project that goes off in a different direction. And then the real project is to find the correspondence between these two projects that I'm setting up. So well, let's just again restate what the first project was. So the first project was to think about this zeta type for G torsors in terms of the I guess you said holonomy. I was having more fun saying monodromy. Somehow that seemed more amusing to me than holonomy. So for being, but they're basically the same word, right?
Yep.
Okay. So what we've been discussing is what I've been calling the Frobenius monodromy viewpoint, or the Frobenius holonomy viewpoint. And perhaps that's also in some sense the geometric viewpoint, because it's based on this intuition about, you know, thinking of the spectrum of a finite field as being a little miniature circle or something like that, some sort of perverse, peculiar circle. Or finite cousin of a circle or something like that. And now we're going to have this second viewpoint, and that's going to be a whole other project. And then we're going to try to have the correspondence between the two viewpoints. And in some sense, this correspondence is, I think, supposed to be sort of like a local or hyperlocal version of the basic correspondence that becomes the Artin reciprocity theorem.
Okay.
That's my plan. So, right, the first project was sort of the geometric way of thinking about it. This second project is sort of like the algebraic way of thinking about it, algebraic in some sense. So what am I trying to say? So it's like, so let me see if I can let me see if I can come close to saying this the way I should say it. Let's see. So how do I do this? What am I trying to say? I'm trying to remind us now of a viewpoint that we've already talked about a bunch when we try to classify Z mod 3 torses. When I try to classify, again, this whole approach that I'm taking now is, you know, it's an attempt at a dignified retreat. You know, I think I sort of have this picture in my mind of how to classify Z mod 3 torses over number fields, but it's such a conceptually unwieldy picture that that's what I'm trying to retreat from in a semi-dignified way. And where I'm trying to retreat to is to this classification of Z mod 3 torses over finite fields instead of over number fields.
Okay.
And, you know, the safe retreat is supposed to be, sorry, it sounds like I just used, so is that true? The word retreat is like the same word, whether you use it as a noun or a verb or something like that. You retreat to a retreat. That's what I seem to be doing.
Yeah.
The retreat that I retreated to is supposed to be sort of this local or perhaps hyper-local version of the thing that I retreated from. It's sort of supposed to be the global version in some sense. That's the plan for how this goes. So I'm trying to recall ideas that we've talked about here when I was thinking about the number fields rather than the finite fields. So the idea goes something like this. What am I trying to say? That every Z mod 3 torser is secretly going to have something to do with the cube roots of something. But there's all sorts of little twists and technicalities in the story, and we have to try to clarify that. So yeah, so for the moment, let's have F be a finite field. And it probably doesn't matter that it's finite at this point, because this is, you know, I'm trying to repeat a story that we talked about when F was a number field, but now it's supposed to be a finite field. Probably the story still goes roughly the same way. I think I'm hoping that it goes it goes the same way. I'm hoping that it's not a lot worse for the finite fields. Them being characteristic P. I hope it's still gonna work. But there are, again, I'm being sloppy here, so there are all sorts of issues here. But let's think of this as a conjecture at this point that we can experiment with. So let's say that we're going to take GL1 of F. Well, except we're not going to quite do that. We're going to take GL1 of F tensored with the Eisenstein integers. Okay.
Okay.
And then we're going to tensor this with Z mod 3. And by tensoring this, you know, so this, right, the GL1, that was an abelian group, but we tensored with Z mod 3, so it's now a vector space over Z mod 3. And because of the way the Eisenstein thing figured in there, this vector space has an involution on it, a linear involution. which perhaps we're taking advantage of the fact that linear involutions act nicely over Z mod 3, over the field Z mod 3, that right, maybe I should maybe it's slightly preferable if I don't know if this, maybe it's slightly preferable if I say the 3-element field instead of just calling it Z mod 3 or something like that.
Yeah.
So I'm just trying to emphasize that it's a field. So it's
Yeah.
giving us linear algebra over a field, which means vector spaces, which means diagonalization is supposed to work reasonably nice. In this particular case, it could work reasonably nice. So, so this involution just has two eigenspaces, the one eigenspace and the -1 eigenspace. So that sums up the whole involution. And it's this, involution coming from the Eisenstein conjugation.
Uh-huh.
And it's the -1 eigenspace of Eisenstein conjugation.
So you said it's the -1 eigenspace. What's the -1 eigenspace? Or are you just saying consider the -1 eigenspace?
Yeah, I'm not sure what I'm saying. I think I'm saying consider that -1 eigenspace of Eisenstein conjugation here.
Okay.
That will be I think that will be a very explicit classification of the Z mod 3 torsors. I think, yeah. Let's call this conjectural at a moment, because again, I'm a little bit worried that I may have done something evil when I jumped back and forth between the integers and the rationals or something like here. But I'm hoping it's going to work. And that, yes, so the idea is that this eigenspace is supposed to give us. Wait, can I think for a moment? Let me think for a moment. Did I say this correctly? I'm hoping I said it correctly, that eigenspace just is the classification of the Z mod 3 torsors over F. But it's supposed to be very explicit in the sense that the way that you interpret such an eigenvector as being, the way that you interpret such an eigenvector as giving you a torsor is that you take, I want to say something like you take the cube roots of, that element. Well, I mean, right? I mean, it's like a. I mean, since we tensored with, am I saying this right? What am I trying to say? I mean, another way of expressing this idea of tensoring with F3, right, is we're saying that we're considering two elements in this GL1 to be equivalent if they differ by a cube. If they differ by a cube factor, a factor of a cube.
Nope.
And so I'm trying to say that it's you can create an explicit torsor from this data. And what I mean is, I guess from this data, I mean before you apply this equivalence relation where you consider things equivalent if they differ by a factor of a cube. So if you have that, explicit element, you can take the way you do it is you form this torsor. You can think of it as a little algebraic variety or a little what do we call those things? Special commutative Frobenius algebra of a certain kind. And the way you form this special commutative Frobenius algebra is by taking the algebraic variety of the formal equivariant cube roots, or maybe I should say equivariant formal cube roots of this element of this GL1. So right, we did go through this in some hideous detail at one point, and I think I still understand it. But when I remind us of it now, it perhaps doesn't sound terribly beautiful, but it's not supposed to be that beautiful at this point. It's supposed to be very explicit. This is giving us a very, if we do this right, this gives us a very explicit a very explicit construction of all the torsors over this finite field F. So right, in some right, the whole meta project of building this correspondence between the two projects is right in that first approach we just had this Frobenius monodromy. In the second project, second viewpoint, we have this explicit torsor. And it's given by this, this explicit sort of cube root that we're taking. And what we're trying to do is establish that correspondence at that level. And, this is the thing that we're going to try to globalize into the whole Artin reciprocity there.
I'm forgetting how, or maybe that's the point, but I'm forgetting how why we think this is going to give us torsors, Z-mod 3 torsors. I know we spent weeks talking about it.
Well, okay. I don't think it's that bad. I don't think it's that bad if you try to ignore a lot of the details. So, what am I trying to say? That well, let me mention some of the ridiculous magic buzzwords that we use. So it's this sort of one of the magic buzzwords was Galois descent. And that involves the role of the Eisenstein integers here. That what am I trying to say? That involves the way that the representation theory of Z-mod 3 becomes much nicer after you algebraically push forward or geometrically pull back. So that's kind of a descent process. Or sorry, that's the ascent process that you're going to descend against. If you the representation theory of Z-mod 3 becomes easier when you algebraically push forward to the Eisenstein field. Here I'm algebraically pushing forward to the Eisenstein integers, but I hope it's still going to work in about the same way.
So a representation of Z mod 3 over F tensor the Eisensteins. Okay, is supposed to be just an element, an invertible element of F tensor the Eisensteins, which you think of as corresponding to the generator of what the generator of Z mod 3, how it acts on a one-dimensional vector space. So all the representations of Z mod 3 over F tensor the Eisensteins are supposed to be one-dimensional, and the representation is determined by the generator of Z mod 3, which will act as some invertible element of F tensor Z mod, sorry, ZE, the Eisenstein integers. I was going to say Z mod E. Okay, so, but two of them count as isomorphic if they differ by multiplication by a cube. So you are tensoring with F3 to make isomorphic ones be equal. So yeah, okay, it is coming back to me, and it is sort of not. I mean, if I'm right, then it's not so bad. One thing, by the way, is that
Yeah.
in our previous approach, in your first project approach,
Yes.
we actually pretty much got a groupoid of torsors, whereas here it seems like you're aiming for just like the set of isomorphism classes of torsors.
No, I think if we do it right, it should work out of the groupoid. But go ahead.
Yeah.
Go ahead.
Well, I was saying that like maybe the groupoid part is the groupoid part coming in with that the tensoring with F3. That is
yes.
Yeah.
Yes. Or so, in other language, it's by the multiplication by a cube factor, by the factor of a cube.
Right.
So those cube factors are the automorphisms.
So you could make a groupoid that would be GL1 F tensor Eisensteins as objects, and then the morphisms, all isomorphisms, would be
yes. Not only could you, but you should.
By invertible cubes.
Yes, to a great extent, you should do this. I mean, and
okay.
There's a lot of interesting stuff to be said about that. But yeah, right. The fact that I'm not saying that at the moment is probably just because I'm being very sloppy and stuff like that.
It's okay.
But so yeah, one of the things you're hinting at there, though, if you actually do it in a very nice, careful, good way, is that there are these, affine algebraic groupoids that you're hinting at here, and the concrete groupoids that you're getting, that we're getting here, are really just manifestations of these affine algebraic groupoids that you're hinting at. So anyway, that's one of the things that you're hinting at here. So yeah, and perhaps also just to maybe remind ourselves a little bit. I mean, right? There's this even easier case of quadratic reciprocity instead of cubic reciprocity or something like that. And part of the story about quadratic reciprocity is that what am I trying to say? That the square free elements of GL1 of the field, the square free elements of GL1 of the field, and that terminology square free, right? It's kind of like an evil gauge fixing or something like that. It's, it makes it sound like it's a sub thing, but maybe it's morally more like a quotient thing, or like the objects of a groupoid or something, the isomorphism classes of a groupoid or something like that. But but of course it's fun being evil. So we say that the square free elements of the multiplicative group of the field is like classifying the quadratic extensions of the field or something like that. Did I say that somewhat correctly? So and then we were sort of trying to do the, you know, the cubic analog of that. And, you know, one of the complications that happens with the cubic analog is just the fact that, you know, the representation theory of Z mod 3 is already interestingly more complicated than the representation theory of Z mod 2. That, you know, Z mod 3 has this two-dimensional irrep over the rationals. And, and perhaps even gets worse over the integers, and we may have to worry about that. But yeah, so that's kind of the story of where we are.
Okay.
So,
Yeah.
so, right. So I think to a large extent, you know, it's my homework to kind of go home and do these projects and try to tell you a good, nice story about how it all works out. But let me try to, you know, let me try to, I have a little bit of time left here. I might try to actually use up the time I'm supposed to have here. At least start out trying to use it up. I'm going to flail around a bit trying to, you know, see how this goes. You know, how does the correspondence, how do these two pictures go? Can we concretely see them in examples? Can we get a sense from examples of how the correspondence is going to work? That's what I'm going to flail around trying to do here. Okay.
Okay.
So, so let me try some of that. So what am I trying to do here? So I'm thinking of, what am I thinking of? Like, let's say, let me think for a moment about possibly F5. F sub 5, the field with 5 elements.
Okay.
And if necessary, possibly F sub 25 and F sub 125, etc. And try to think about Z mod 3 torsors over this, okay?
Okay.
So like I say, let me try flailing around a bit here. So let me draw like the origin right there. And draw 1, 2, -1 and -2. And let me try to draw a sort of not quite short in there. I'm trying to draw, maybe I'm trying to draw it right. Maybe I'm trying to take the, first of all, I'm trying to picture Z mod 5 or F sub 5. I'm trying to picture F sub 5 as a quotient ring of Z. And then I'm trying to, you know, I'm trying to think about F sub 5 tensor the Eisenstein integers. And I'm trying to sort of picture that in a good way. So I think what I'm trying to say is that, you know, I've got this sort of lattice. This is my origin right here. But I've got, let's see, 0, 1, 2, 3, 4, 5. So this is also in there. And let's see, 1, 2, 3, 4. I guess up here, I guess. And down here, 1, 2, 3, 4. This, hopefully the picture will get a little bit clearer as I try to draw what's going on. So again, I'm doing this ugly thing of drawing Eisensteinian pictures on Gaussian graph paper, but that's what I'm stuck with for the moment. You know, so try to visualize the whole Eisenstein integer lattice. It helps me if I draw a little bit more of it. And yeah, now I'm trying to sort of draw the Voronoi stuff for this lattice. Voronoi in some sense. So what am I trying to say? I'm trying to say that like there's like, you know, that's the sort of boundary between this region, the region centered here and the region centered here, and there's like a boundary here. And there's like a boundary here. Where is it? Like here? Might seem like I'm drawing the right. Let's see. Maybe I should. Yeah. Okay. Let me try it this way. Maybe I should. What am I trying to say? So how did it go? It went like this, and like, what did this do here? This one went between here and here. And did it go there? I guess it did. I guess it went like that. And then this one goes here. And this one goes here and here. And what does it do? Where does that one go? I guess it is right there in the middle. Okay. And then it goes down here. Kind of there, and then that's right. You know, so I'm trying to get this picture of the. I'm trying to get this picture of this. I'm trying to get a reasonable picture of what this finite ring looks like. So it's like the Eisenstein integers modulo the ideal. You know, it helps me if I can see what this finite ring is like. This quotient ring. So, you know, this is like representatives for the cosets of this lattice. And of course, there's a little bit of funny thing on the boundary where you still have to. So like, let's see. So there are these unambiguous ones in the middle, which is what? It looks like there's 3, and then 4 is 7, and 5 is 12, and 4 is 16. So it looks like there's 19 that are unambiguous. And then that leaves 6 that are a little bit ambiguous. It looks like there's 12 of these here. So how do they match? How do these match up? It's like, I guess you just jump to the other side or something. What am I trying to say? No, what do you do? What's the identification of these 12 points on the boundary of this little Voronoi hex? I guess you can see. Am I seeing that right?
I think they're identified with the points on the opposite side. No.
Yeah, it seems like this point is the same as this point.
Yep.
This point is the same as this point. Oh, and this, so this point is the same as this point over here.
Yeah. So they're half as many in reality.
Right. So if I wanted to take
so there's 6 of them.
Yeah, so I could just have them be on the right half or something like that. I could take the favored representatives to be on the right half. Okay. And now let's
so there should there be 5 squared points total?
Yes, 19 plus 6.
Okay, good.
Like I said, there's 19 safely inside.
Yeah.
And then
but also just by, that's good, yeah. But also just by some other way of thinking, you know that it's a
yes,
quadratic extension of F5 or something like that. So it's
you're just tensoring this 5-element field, but yes, that's right.
yeah.
It's
Okay.
two-dimensional vector space. That's right.
Yep. Okay.
And okay, so we've got 25 elements. Now, how does this one work? So, right. So is this split or is this? I think, is that right? So F5 seems like it doesn't have. Yeah, I think that's right. I think right. It's the primes that already have the cube roots of unity in an unramified way are the ones that are equal to 1 mod 6. And the ones that are equal to -1 mod 6 are the ones that don't have the. So I guess we're saying that this really is a 25 element field. So I guess I guess this really is F sub 25. All right, now what were we supposed to do? We're supposed to take, okay, so F sub 25, so that means it's got a 24 element multiplicative group. So, okay, we've got GL1 of F sub 5 tensor the Eisenstein integers. So this thing is a field. So this is just a cyclic group, and it's 24 elements. Because it's 25 element field, so the multiplicative group is just 1 element short of the whole field. Just okay. So that means how is this working? So what happens when we So when we tensor this cyclic group with F sub 3, we get a 3 element thing. Right? So we're saying that yeah, we're saying that there are three equivalence classes here of these 24 elements. And yeah, there are three equivalence classes of these 24 elements. And let's just make a very quick attempt to see if I can find in my notebook a picture of where these three equivalence classes are. I'll give up if I can't find it, but I actually did have a picture here. Let's see. Is that the picture? Let's see. What does it look like? I think I accidentally turned to the correct page, but right there, let's see. One, two, three, four, five. Okay, that's 7. This is 1, 2, 3. 0, 1, 2, 3, 4, 5. Let me try. let me see if I can get this to work. So they seem to be getting that one of the equivalence classes looks like these 6 elements. And then what? How does that work? Maybe it's like there? And then another one is these 6 elements. And why is there only 6 elements there? There should be 8, right? What is? Wait a minute, I'm not sure I drew it correctly. Let me. All right, first of all, can we, okay, we're getting really close to quitting time here.
Yeah.
Could we just pause for about a minute and I'll be back?
Okay. Okay, we're back.
Okay. I'm just trying to wrap it up right now. I'm just trying to give you an idea of what I'm going to be trying to do, in my next attempt at telling you about how the projects are going. So I did make an attempt here to copy from my notebook a little bit picture here, which is supposed to show the 3 different equivalence classes, which give you a very explicit classification of the 3 torsors over F sub 5. The 3 Z mod 3 torsors over F sub 5. So it's, I don't know, if you stare at the picture here, you can see there's red ones and green ones and blue ones, and those correspond to the different things, the different Eisenstein quantities that you can take the cube roots of. And so there's some mysterious correspondence where these 3 different colors correspond to the 3 different Frobenius monodromies. And that's what I'm trying to clarify. So that's what I'm going to go home and work on and think about, and try to report on when we talk about this again. So yeah, we'll just have to quit there for right now. And thanks a lot. And I'll see you later.
Okie doke. Sounds
Okay.
great.
Bye.
Yeah, I'm just gonna sign off.
Okay, sure.